NJ4Z here, and welcome to my Hamshack here in Rock Hill, South Carolina. It's been a while since I've done a video from the Hamshack. Been very busy the last 18 months or so, probably a little less than that, maybe a year, 12, 14 months with the club. I took over as communications director after stepping down for president, so that took a lot of my time, and I apologize for not doing a lot here, but I'm back in the saddle and getting ready to start doing a little more video from the Hamshack, and looking forward to getting the channel going again. So welcome back, and it's good to be back. So let's start talking a little bit about solar weather and its effect on amateur radio. It's November the 6th, 2021, and we've had the last week's been a real roller coaster ride with solar weather. We've had quite a few solar flares, some big ones, some long, what do they call them, long duration flares, and we've also had some big CMEs hit the Earth. And that's kind of had the ham radio bands torn up. And I've noticed on Facebook and a couple other social media places, and I've also in our club, people have been asking about what happens and why does this happen with solar weather. So let's go back to what we learned kind of when we were undertaking our studies for the license testing. Okay, so we'll talk about the basics of solar weather. So right now you have the sun and the earth, and the sun itself puts off energy, the solar wind. So not only do we get light and heat from the sun, but we get all kinds of ions and electrons and cosmic rays and X-rays, UV light, all those different radiation types that are banned, the full spectrum, ultraviolet, all infrared, you know, all of that. And then we have the Earth. In the Earth, we have our atmosphere, which is made up of various layers. And one that's important to us is the ionosphere, because we use the ionosphere as ham radio operators for HF propagation. We use the ionosphere as a reflector, basically. So we also have to talk about the ionosphere. You know, it's not a shell. So if we take a look at the ionosphere as a whole, it's more like cotton candy than the shell of an egg, okay, with the Earth as being the yolk, and then the shell of the egg, and then, you know, the other parts of it, magnetosphere and all of that. And the ionosphere is broken up into several layers, okay? So you have the D layer, the E layer, the F layer, which is actually F1, F2, and there's actually an F3, but we don't really need to concern ourselves with that. The ones that are really important to us are D, E, and F, 1 and 2. Okay, so on the daylight side of the Earth, sunlight is striking the Earth. It energizes the D layer, the E layer, and the F layer. Depending on how much energy, it's not actually the sunlight, it's solar energy in itself, the solar wind. How much X-rays in that, how many high energy ions, high energy electrons, all those different things energize the atmosphere. So when you get high X-ray flux and high UV flux coming in from the sun, that charges up the D layer. And the D layer is kind of the enemy here because it tends to absorb RF for us. So when we have high D layer activity, basically it absorbs our HF signals, so they have nowhere to go. They just get eaten up, okay? The E, we know, is the higher frequency stuff, so 6 meters, 10 meters, 12 meters. Those tend to reflect better off the E, hence the term sporadic E. And then you have the F layer, which is the primary mode for us to bend our RF back to Earth, okay? So at night, the D layer kind of goes away, the E layer kind of goes away, and the F layer collapses from F1, F2 to just F. So, but we have to think of it, it's not a solid sphere, it's cotton candy, right? So that's why propagation in one area might be really good, propagation in an other area may not be good. It just depends on where those X-rays are and how they hit the atmosphere, how that UV light energizes the atmosphere, okay? So, as we know, as ham radio operators, we are going into solar cycle 25. Big deal been made about it for about the last 6 to 12 months. Everybody's, oh, we're in cycle 25, you know. Well, what does that mean? So every 11 years, the sun goes through a solar cycle. And that's basically the reversal of its magnetic field. So now north goes to south and south goes to north, and vice versa every 11 years. During that time frame, while the magnetic field is moving, you get concentrations of magnetic flux along the surface of the sun. Those areas get dark. They put off a lot of UV energy, a lot of X-ray energy, and they're called sunspots. Okay, so when we get the high UV and the high X-rays coming off those sunspots, well, that energizes our ionosphere and helps us propagate signals. Okay, now we are just going into the solar cycle. We've come out of solar minimum. Okay, so the last 2.5, 3 years, 2018, 2019, well, last half of 2018, 2019, 2020, were pretty crappy on the bands. That's why what is it? The FT8 and FT4 took off, because it was weak propagation, weak signal, and propagation was enough to support those. But now we're coming in solar cycle 25, and we're starting to see the sun wake back up, right? Because when you have sunspots, you can also have solar flaring. Okay, so when those magnetic fields get complex between the sunspots, and things don't go exactly as planned, as magnetic fields touch, they explode and cause a solar flare. Okay, along with solar flares, you have CMEs possibly. You also have something called coronal holes, which are basically spots in the corona on the sun where it's not as dense. So the solar wind coming from, and the corona is actually kind of like the surface of the sun. So when you have a coronal hole, the solar wind comes out a lot faster, and that can play a little bit of havoc with the ionosphere as well. And then when you have solar flaring, okay, so solar flare, as soon as we see that flare on Earth, the visible light from that flare, we've already been impacted by the X-rays that are coming with that, and that can cause HF blackouts on the sunlit side of the Earth, depending on how severe the solar flare is. Along with that, a day, 2, 3 later, depending on the speed, we may see a coronal mass ejection, and that's when you have plasma and ions and denser material, not X-rays and UV rays and visible light. These are going to be traveling less than the speed of light, and they're going to impact the Earth. And what that happens is it actually impacts us in 2 ways. One, it plays a little havoc with the ionosphere, and 2, it plays more with the magnetosphere. Okay, the magnetosphere is that magnetic field that surrounds the Earth that protects us from all the dangerous things the sun puts out. Right, so a lot of that solar wind gets absorbed and pushed off, and it's just like a magnetic shield. Okay, so when that gets disturbed, it causes noise on the bands, can cause HF propagation issues at the poles. So, you know, you have some big issues with coronal mass ejections. Okay, so CMEs are not our friend. Although after a CME goes through and we get through the disturbance in the magnetic field, it sometimes leaves us with a little better energetic ionosphere. Let's put it that way. It energizes it, and we get a little better propagation for, you know, a few hours to a few days. Now, so what happens when we do get a CME? Okay, so you can see the CME here as it's coming off the sun, and that's a pretty good example of one that's firing kind of away from us. When it goes around and it looks like it's a halo around the sun, that's one that's aimed directly at us, and that's not a good situation. But what happens is when that field hits us, it squeezes down the magnetic field, and you can see it pushing in, and that disturbs, obviously, the magnetic field of the Earth and causes us problems on the HF bands. Okay. Also with that, you can have ionic storms. So basically at the north and south pole, you have the magnetic fields fold in, on each other. Okay, as you can see here at the North Pole and here at the South Pole, the magnetic field pushes in, and that allows high energy particles to stream in along those lines into the polar regions. And when that happens, the atmosphere gets really churned up, or the ionosphere gets really churned up, and it can black out HF communications. And it can, once it gets inside there, it can, depending on how severe it is, it can come down some low latitudes. So, 49, 50 degrees would be very severe. And we would have some serious problems with HF and radio propagation, not to mention the GPS satellites, communication satellites. Yeah, we'd have some serious problems. But we look at those as they're severe ones are pretty rare occasions. Okay, so let's talk about how we can find out about what the solar weather is going to look like. So there's a website that's run by NOAA, which is the National Oceanic and Atmospheric Agency, and that's a government agency. It's a bunch of scientists, and they're responsible for not only weather here on Earth, but space weather. So let's take a look at their site real quick. So I'm going to pull up their site, and there it is. Okay, so it is the Space Weather Prediction Center. So if you want to use the URL, it's www.swpc.noaa.gov. Okay, and up at the very top, you have the current conditions, and they use things a little differently than you see in most ham radio sites, and we'll talk about that in another video. I'm going to give you the basics here, and then we're going to do another video with some of the more information about how to use this to predict propagation, and what days are going to be good, what days are going to be bad, and what those things mean in the widgets you see everywhere. So at the very top here, you have the 24 hours, the latest observed, and the predicted. Okay, so let's talk about the R, S, and G and what they mean. R is radio blackout conditions. Okay, and it's scale 1 to 5. And that's basically due to solar flaring. Like we talked about, when we see a solar flare on Earth, it's already happened on the sun 8 to 8.5 minutes ago, because light travel, the time it takes light to travel from the sun to the Earth is about 8 minutes, okay? Because it travels at the speed of light. Along with that, X-rays and UV rays and all the high energy particles that are radiation type particles, UV, those kind of things, are all traveling at the speed of light. So it's an electromagnetic wave. So when those things hit us, it's already happened 8 minutes ago on the sun. So when we see the flash, we're already being affected by the X-rays and the UV light. So when you get that, you have different classes of solar flares. You've got A, B, C, M, and X. Now, why they skip D, E, I don't know. But you have A, B, C, M, and X, and that's an ascending scale. So an A is the lowest, and X is the highest, and there's different values associated with those flaring. So you can have a C9, an M9, an X9, and it's an exponential scale of power that's released from the sun with those flaring. Okay, now S is for the ionic storms. We talked about that just a few minutes ago. When you have those abundance of protons, electrons streaming into the polar caps, that's when you get the solar storms. And those are 1 through 5. Okay, so those are basically ionic storms. And then the G is the geomagnetic conditions. Okay, and that's on a scale of 1 through 5 as well. Okay, 1 being the least severe and probably normal, and 5 is the most severe and would cause us some major issues here on Earth, because the geomagnetic field plays a part in our grid security, so electricity. Okay, the Carrington event in 1859 was a very large solar flare that also had a huge CME with it. The CME hit the Earth. It was a very strong CME. And basically, it screwed up the magnetic field enough where you had telegraph wires catching on fire, people being shocked from telegraph keys, stuff burning down because of induced currents. So if that was back in the 1859 realm before we had real electricity, can you imagine what one of those storms would do today? Um, Basically, we would be put back to the mid 1800s or earlier. We would have no electricity, or part of the earth would have no electricity. Transformers, generators, all the electronics, anything that's dependent on electricity would pretty much, if it's not protected by a Faraday cage or disconnected and lucky, it's going to get smoked. So, yeah, we never want to see a level 5 geomagnetic storm. That would be crazy. Basically, SA, what is it? SHTF at that point in time. So, um, yeah, we don't want to see one of those. But there's also some really good information, and that's what's happened in the last 24 hours. Then you have the latest observed, and then you have the predicted. Okay, and the predicted is going to be what kind of solar flaring they're saying and what kind of geomagnetic storm is possible over the next 24 hours. Because again, we talk about the geomagnetic storm, it's the solar wind that can cause that, the enhanced wind from the coronal holes, and then a CME. So any of those can cause geomagnetic storm. Okay, so they give us the probability of the radio blackout and the geomagnetic storms. So right now we're looking at this, and there's a 5% chance of a radio 1, radio 2 blackout. There's a 1% chance of a severe radio blackout, and about a 1% chance to have anything higher than a geomagnetic storm situation. Okay, so this site's very useful. It's got some dashboards, and these dashboards are all a little different for different things. One we'll probably want to look at more often than not is the radio. Okay, this box here, the D absorption, we talked about how the D layer absorbs when it gets over energized. Okay, so this is actually a little bit of a, I guess, a GIF. But you can press the button and it'll start to download, and it'll play. And what you're looking for here is if there is any solar. See that right there? So if we go back and look at that, let me pause it when it gets there. Okay, so that was a solar flare, and it's probably associated with one of these C-class flares here, okay, that caused it. And that's a radio blackout. It's very minor. The dB absorption was less than 5 dB. So this is the dB scale of absorption, and then this is the scale for megahertz of frequency. So as you can see down in the low bands, so 160, 80 meters, we had some high absorption there, okay? And then you see this purple out here, that's, you can see this color goes here, and we had some absorption into the 30 meter band. We didn't quite get up into the 15 meter band, but let's let this roll and see if it goes any further. No, that was a pretty short-lived one. So you can see with this, you have, you know, a good way to see what's going on. But this is real time, or this in the past, so it's not real time. It's not a predictive element. It's showing you what's going on. So if the bands go dead at some point in time, you can go here and look and see and say, oh, well, we had a solar flare, so that's what's going on. Or you can look here and you can see when we pull this up, solar flares. Okay, and we talked about A, B, C, X, and M and X. And you can see these are all the flares over the last few hours. We've had a couple, 3, 4, 5 C flares, which are pretty powerful. Not terribly powerful, but, you know, powerful enough. We haven't had much solar proton flux hitting the polar cap, so it's been pretty flatline. Now, geomagnetic activity, that's what we talked about, the geomagnetic storms. The other day, November 4th, when we had those big storms and the bands were so torn up, this is what we were talking about. We had a KP index of 7, which is a G3 magnetic storm, and that's pretty severe storm. It's not the worst, but it's not a good one either. And it was turned up for a good bit, and now, but it's been below KP4 for the last couple of days. So things have calmed down a little bit and conditions have returned kind of normal. Well, we'll talk about what this K index means. For this video, we're going to be talking about this side of the scale here, the radio blackout, the proton flux storm or ionic storm, and then the geomagnetic storm. So let's get that off of there. Okay. And this also gives you Aurora forecast. Now, this is a forecast. It shows you the probability of seeing Aurora and where it's going to be. So when we get a lot of energy into the atmosphere, especially around the poles, the Aurora will brighten up because it's the interface between the Earth and the ionosphere and the energy coming in. So you get these bright auroras. You've heard Aurora Borealis, and they can stretch down a little bit further. And with that last geomagnetic storm, we had that G3. There were some bright auroras down in the northern parts of Scotland, where you wouldn't normally see them this part of the time of the year, but some pretty amazing stuff in northern Canada as well. And then this just shows you the ultraviolet look at the sun, and you can see where the sunspots are, these bright active regions. There may or may not be sunspots, but that's where there's magnetic activity. And then these dark areas, those are the coronal holes we were talking about. So that gives you a pretty good tool. Now, again, there's other dashboards out here. There's one for electric power, which has another little neat thing, and it's called the WSA Enel Spiral, okay? And this is a pretty cool little app. So when you have a CME or we have enhanced solar wind, this will show you, and it kind of predicts when it's going to get here. So let's let this thing load up and take a look at it. Okay, so we don't have any solar flares on here, at least I don't think we do. But you can see there's some high energy particles here from a coronal hole, and you got another one coming around. This is Earth right here. This is looking down on it like you were a bumblebee flying over it. This is looking at it from the side, and again, this is another view, and it shows basically the same thing, but it's showing you from stereo A and stereo B, which is two satellites that are in orbit. Okay, stereo A is behind us in orbit. It's behind us in orbit, but the sun hits it first because the sun rotates in the direction the Earth moves, and B is behind is in front of an orbit and behind, so it sees the backside of the sun. And then of course you have the other planets out there. But that's basically a very good tool when they're going to show you the plasma density picking up, which is that, CME or enhanced coronal hole stream. Okay, so just some plasma density and relative velocity of the speed that it's coming. Now, that last solar storm that hit us at over 700 kilometers per second, which is about 1.8 million miles per hour. So a lot of velocity, and it was pretty dense, so it churned up the atmosphere pretty good. But that's just something you can take a look at, and you can see if you have a solar flare and you want to see if there's a CME coming associated with it, when it's going to arrive. It'll show you that, and it'll kind of give you it'll look like a waveform coming off of this. But so just so you know, that's just kind of a thing here. And again, here's what we were talking about with the KP index and the relationship to geomagnetic storm. November 4th is when we had that mess, and here it is. We've had some reverberations, all these little 4 kick-ups here. That's all just reverbing from this stuff. The magnetic field's starting to settle back down. Hopefully it'll settle back down and we'll get back to, a G0, G2, G1 situation. And that'll allow us to have less noisy bands. Okay. You can also see, this is the chronograph we were talking about, where the solar flares. If you have flaring, you'll see it on here. And again, you have the same space weather overview and the Aurora prediction. But I don't see any solar flares. I'm kind of looking at this to see, flaring or CME ejections. All these little particles you see that look like snow coming at you, those are high energy particles. They're hitting the cameras for this particular sensor. And why you have this disc here, it blocks out the corona of the sun, so the sensor can actually see what's going on around the outside is what you want to look at. But that's basically it in a nutshell. There's some other sites like Space Weather News that kind of give you some synopsis of things. Also kind of explains what's going on. Do you really need 2 or 3 sources? Well, yeah, sometimes they have some different graphics that can explain things a little differently. I like the NOAA Space Weather Prediction Center, and I love spaceweathernews.com, so either one of those is pretty good. But I'm going to keep this short for today, and we'll come back with another presentation and talk about how we can use this information and the little widgets and explain what those widgets are and how that affects our ability to use the ionosphere to propagate our signals. So until then, y'all stay healthy, stay safe, and stay passionate about amateur radio. This is NJ4Z, and I'm out.